Hello, welcome back to Learn from a Layman. I'm Carl Christensen. I'm back today with Johnny Nielsen, who's been on multiple podcasts. So if you don't know who Johnny is now, then you're not listening to enough of our podcasts. Johnny is, or Dr. Johnny, as some would have him called. And we're back today for our second podcast with Peter Vogel. Peter is our resident physicist, not physician, because that's what Johnny is. Anyway, but we've got a soon-to-be dentist and doctor on the podcast, and therefore we are talking today about relativity, because why wouldn't we? So today we're going to be talking about the theory of relativity, the history of it, the implications of it, and just give you some. Now we've discussed physics in the past. We've touched on relativity lightly, but this is going to be a more in-depth dive into all things relative. So let's go ahead and get started. The history of the theory of relativity. Now, from a layman aspect, I think most of us just assume that Einstein was the sole creator of all things theory of relativity. But Peter, you want to give us a slightly more nuanced take on how the theory of relativity came into being?
Yeah, so relativity was discovered by a couple people simultaneously. Originally, special relativity was discovered, and then general was the second one to be discovered. But Einstein and a different scientist called Lorentz came up with the idea that time might not be advancing uniformly for everyone and everything. It explained a lot of things that were going on in physics that were just unexplainable at the time, and at the time people thought that pretty much everything in physics had been discovered. There were people who were being told to not go into the field because there was nothing left. So relativity kind of opened the floodgates of realizing that we didn't know everything.
That's really funny.
So some of the most famous physicists actually ignored the advice of their advisors and other people in the field because they were like telling them that there was nothing left to be learned.
Interesting.
Yeah, anyway, basically, Lorentz discovered relativity in a different way from Einstein. Einstein realized that time doesn't advance uniformly, and he developed some formulas that work with time and speed. And Lorentz developed another one that we use both because they're both useful ways of thinking about it. But Lorentz, his formulas were not so much just directly correlating speed and time, but so much as correlating position and space-time and deriving formulas that really connect what space-time is and how space and time are not really separate entities but one.
So yeah, I think you already mentioned this, but that they didn't collaborate on this, right? So they're working independently of each other. Lorentz, a Dutch physicist, I believe, so working in the Netherlands. Einstein, originally German, but I believe at the time that he was discovering relativity and doing those formulas, he was living in the United States. Came to the theory of relativity almost simultaneously, but without collaboration, right?
Yeah, they came up with it almost at exactly the same time, and they came up with it in different ways. But
Right.
special
Yeah.
relativity really was doomed to be discovered. There were lots of people working towards
Okay.
that. General relativity was kind of more out there.
Right. Now, special relativity was discovered first and then general relativity. So is that the order it came in?
Yeah, seems kind of backwards, but yeah.
Yeah, you would think so, right? Just the naming would seem to indicate that special would be the progression of the theory of relativity away. But yeah, let's talk a little bit about I guess the differences between. I think you've already started touching on special relativity versus general relativity, but from the layman point of view, you know. I guess the layman doesn't really actually differentiate at all. And if you hear the difference between special relativity and general relativity, um, me without a lot of physics background, I know that one of them has more to do with accounting for gravity. Is that right?
To really dumb it down, basically, special relativity says that the faster you move, the shorter you get, and the slower time moves. for you compared to everyone else, however it advances normally for you. And then general relativity is the more gravity, like the deeper in the gravitational well you are, which we can talk a little bit more about later, but basically the more gravity that is being exerted on you, the slower time moves for you. And that goes down to, like, if you go up into the mountains, it's a measurable difference that time is moving slower for you than other people.
Yeah, and that's something I wanted to touch on. So we can actually just do that now. I mean, if we're talking about so general relativity deals with that time dilation effect, and you're saying that's measurable even at uh, the level of gravity that we experience here on Earth and the speeds that we deal with here.
Yeah, it is technically measurable.
Okay, but yeah, we're talking
Not
like
to any
fractions.
normal person.
Right.
Yeah, I mean,
Right.
fractions makes it sound bigger than it is. It's like femtoseconds. So like,
Okay. Right. Yes.
yeah,
Good point. Yeah, we're talking about incredibly small numbers, but yeah, I mean measurable, and so that we can actually figure out. Okay, in femtoseconds, this is the number of uh, the difference between being on a mountain versus being at sea level or whatever.
it's measurable enough that they have clocks precise enough to tell the difference, so they can see that time moves slower, like on a mountain than at sea level, but not measurable enough that anyone would ever notice.
Right.
Um,
Now,
that
why
includes
did?
speed. I don't think we have anything fast enough to actually notice. So,
Oh, okay. That makes sense. Now, we'll talk a little bit more about that in a minute. But okay, so as far as once again, just revisiting special relativity to general relativity, when Einstein um, had the formulas worked up for special relativity, was developing that theory. At what point did this concept of needing more, what was it that prompted general relativity specifically? Was there one thing that was missing that he noticed, or I guess you said that this deeper gravitational wells, was he in a particular formula or trying to account for a particular effect when developing general relativity?
um, I'm not positive on that. I know that general relativity filled in some of the gaps that people didn't understand. I think he was kind of trying to figure out why, like, general relativity kind of explained why light was affected by gravity, because light has no mass,
Right.
and hence gravitational force is governed by the equation force equals the gravitational constant g times mass 1 times mass 2 divided by r squared. And if mass 2 is 0, then that force is 0. So Einstein was kind of trying to figure out why light was bending around things. It didn't make any sense with the physics that we had at the time.
Yeah. Yeah. That okay. So these are a few of the questions that really, when I was starting to think about this podcast, that the layman, once again, I represent that person, um, doesn't. A lot of these concepts are just hard to even conceptualize. So okay, but before we get to light and why it bends, and you already started explaining that, but as you get close to the speed of light, even the layman knows that mass increases, right? As you get closer to the speed of light, uh, mass exponentially increases, right? Which is why we can't get to the speed of light. Is it would take infinite energy to get a mass, a particle with mass to the speed of light. Um, why does
Mhm.
that happen?
Um, there's actually two ways of thinking about this. Some people think that mass actually increases. Some people think that it's not mass increasing, but that it just takes more and more energy increasing exponentially to accelerate once you're going that fast. So, one school of thought, yes, is that as you go faster and faster, you become heavier and heavier, and thus the equation governing like kinetic energy, it's like 1/2 mass times velocity squared. The velocity obviously is governed. It has a speed limit of c squared, or the speed of light squared, but mass, if that equation is going to run away to infinity, mass is the only other factor in there that can increase. So some people assume that mass just increases till you're moving something that's so massive that it can't go any faster. But that's once again why light can do it, because light has no mass.
Right. Now we can get like neutrinos, which have mass, to like some incredibly high percentage of the speed of light, right? I think last podcast we had you on, we talked about CERN, the particle
Mm-hmm.
accelerator over in Europe, that and we
Yeah.
can get those particles that have a measurable but essentially infinitesimal mass to like 99.99 the speed percent of the speed of light. Is that right?
Mm-hmm.
And so we don't, because their mass starts off so tiny, that's why we can get them so close to the speed of light.
Um, yeah, in part, they're also a lot easier to accelerate just because they are smaller. So yeah, I guess the mass would be what's um, what's going there. But
Okay. And so is that, I guess my question is, so we can measure the effect of accelerating near to the speed of light on those particles in these particle accelerators, and so we can measure some of these effects of relativity just based on what we can observe from those particles.
oh yeah, I mean those ones are actually pretty significant. Some of those particles that they're accelerating last like millionth billionths of a second, which is
Mm,
um, pretty long for some of those particles. But when you accelerate them to like near the speed of light, they actually last for a couple of seconds,
wow.
which is a huge difference. So
Yeah.
even particles coming in from space, sometimes there's particles that'll come in from space, and if they were to not abide by special relativistic um, laws, then they would disintegrate in a fraction, and a fraction is being generous of a second, where they actually can make it all the way to the surface of the Earth because of special relativity. Because in their frame of reference, they have only lived for their allotted amount of time, but from ours, they lasted way longer than they should have.
Okay. Interesting. I didn't know that. Um, Okay, so these neutrinos, which you said are tiny, some of these particles that have just essentially that don't exist for more than generally wouldn't exist for more than a millionth or a billionth or femtoseconds or whatever. Um,
Yeah. Neutrinos
they're
actually last quite a while. Neutrinos
oh,
aren't unstable. I mean, the sun emits neutrinos and they pass through the Earth and they go on for a long time. They're pretty stable particles, but there's other ones
okay,
that we can make that aren't so stable.
got it. Okay, now so these are all particles we're talking about that have mass. And that therefore we can deal with and we can accelerate and can't get to the speed of light but can get close. You mentioned light, and light is the part that I guess I don't fully. So I know that light can act like a particle. We have photons, right? Particles of light, and they can go the speed of light, obviously, because they're massless. But how do you have a massless particle? To me, that seems like an oxymoron. A particle to me seems like something that exists. A massless thing like a wave makes sense to me because that's more of a pattern of energy movement. A particle itself seems to me like it would have to intrinsically have mass in order to be a particle. Otherwise, it's like a pattern or it exists as energy only.
Mm-hmm.
So how does that
Yeah,
work?
it's a packet of energy. So mass and energy are kind of interchangeable to some degree, which is one of the other things Einstein developed, his E equals mc squared equation. You can turn
Right.
mass into energy, but light is originally they thought it was just a wave, which um, made a lot of sense and it seemed to work most of the time, but it really confounded physicists a lot of the time when light didn't act like a wave, when it acted like a particle. And um, so there's something called wave particle duality, and people just don't like, you couldn't describe light solely as a wave because it had particle properties. But it's a packet of energy. It's called a photon, which I'm sure everyone's heard before, but it's not, there is no mass, but it's a packet of energy that's just moving.
Okay. And
So
so
in a sense, yeah, there's no mass to it. A particle seems to like it would have mass, but
if light exists, it has energy and therefore it has photons. And okay, I think I better understand how that works then. So that the only way that you can't have a stationary photon then, right? I mean, it has to be traveling.
yep.
Okay. All right. Well, that kind of makes sense. And as if a photon is traveling at the speed of light always. Is that right?
hmm Yep.
Okay. Because it is energy of light. Okay. So let's talk a little bit about the space-time continuum. So we started talking about you've mentioned that originally with Lorentz and Einstein and what they were measuring and how gravity affects time. But why is it called a continuum, and how does that work?
Um, a good way to think about space-time, it can be described as like if you were to stretch out a big piece of rubber or a tarp or blanket or something, and then if you like put things on the blanket, they make kind of a divot around themselves. So the rubber or blanket, we'll just call it a blanket for now, um, is what we would describe as space-time. So as you move deeper into those wells that like your little ball or whatever you put on the blanket are making, the deeper you move in, the slower time moves. So we have three dimensions, like X, Y, and Z. And then you also have a fourth dimension, which is time. So depending on if you're talking general or special relativity, as you move faster and approach the speed of light, your fourth dimension becomes a lot more important because, for example, if you are a photon of light, you um, time no longer advances for you because once you travel the speed of light, time is stopped for everyone outside. So you're now traveling more through time than you are through space from your frame of reference. It's kind of difficult to think about. So I think going back to the blanket analogy, um, if you think of the blanket as three dimensions, which you kind of have to wrap your mind around a little, it's um, the deeper you go into those wells that are made by the heavy object sitting on the blanket, the slower time moves. So it's kind of just a fourth dimension that you have to think about while um, doing equations. It's probably the easiest way to think about it. Lorentz has some equations that describe it better, and you can make like space-time charts that plot object's position and time relative to it because once you're moving at relativistic speeds or at relativistic gravitational poles, once you're in those um, gravitational wells, then time is no longer a constant that you can just depend on.
Right.
I don't
So
know
I
if
guess
that made
that's
sense.
it does. Well, I mean, it does in as much as relativity can to a layman. Uh, but the idea that, yeah, that moving at the speed of light means that you're moving in time no longer, or you're moving, yeah, you're moving in time. You're not moving in space. I I
hmm
mean, it's really hard to conceptualize for me because I guess uh, why is it that that speed um, means that you're no longer dealing with the other dimensions, essentially. Uh, Does that?
Yeah, yeah, and it makes sense the question you're asking. You and um, probably a lot of people that listen to this know what an asymptote is on a graph. It's kind of where you
Right.
run to infinity.
Mhm.
But um, c, or the speed of light, is when you reach that asymptote. So
Okay.
the speed
Right.
of light, or another way that's maybe easier for some people to think about because they've thought about it before, is like once you go, once you hit a black hole, time stops advancing. So um, there's like the event horizon is where now your time is going infinitely slow for you and infinitely fast for everyone outside. So someone watching someone who goes into a black hole, assuming they survive, um, as soon as they cross that event horizon, the person going through the black hole would continue at their current speed or acceleration or whatever. And to them, they would see themselves as just going across it and coming out the other end if they could escape it. But the people on the outside, they watch them go in, and as soon as they cross the event horizon, time just moves infinitely fast for them, so they cease to exist in the universe to some degree because time has just, all of time and space has passed since they crossed that horizon.
Mm.
So they'll never come out again. Once, like light, the reason light can't escape a black hole is because, once again, like light isn't affected by gravity. It could just cross a black hole and go straight across and never even know the difference in its frame of reference. It would take a nanosecond to cross that distance and then come out the other end. But when we watch it cross that event horizon, it crosses and now it never is going to come out again, because as soon as it crosses, now time is infinitely slow or infinitely fast. All of time has passed for that photon, and now it's just gone forever.
Okay. And taking it back to your blanket
So what?
example.
So I have a question.
Go
So
ahead.
which viewpoint is actually real?
They're both real
Like,
depending on
is
who
the
you are.
photon actually gone forever?
Yeah, so relativity is relative to the observer. That's the whole idea behind it. So say you were in a spaceship that could go at almost exactly the speed of light, and you flew into that black hole and somehow were not affected by the gravity of the black hole. In your frame of reference, you would go in and come back out the other side and not know any difference, except that when you came out the other side, I don't know what would be left, because all of time outside would have advanced. So from your perspective, um, time is advancing normally. Your watch would tick normally. Everything would be normal. The people watching you would see time moving much. Well, okay. I guess that's a problem, because now we're moving at the speed of light and crossing an event horizon. So yeah, that makes a problem for us. But essentially, if you move, I guess this would be a good time to talk about like the twin paradox. I don't know. It's
Yeah.
kind of a common paradox that people have heard of, but the idea is that if two twins were born on Earth and one got on a rocket ship and flew to Alpha Centauri and came back, then the twin that stayed on Earth would have aged, and the twin that flew to Alpha Centauri and back would not have. So he would be, I don't know, say one twin had aged to the age of 80 and the other had, and they parted when they were 20. The other one might come back at 22, and the other twin would be 80 years old. So for like your question about which one's real, both are real. For the person on the spaceship, they just, like, their time seemed to advance normally, but when they got back, time on Earth had advanced much more rapidly for them, for the people there.
So this reminds me of the movie, which I think may have come up in the past in one of these podcasts, the movie Interstellar.
Yeah,
Right.
it's really well done.
Yeah. They deal with all of these issues, right? I remember specifically one scene of that movie where they are trying to figure out if one of the planets is habitable, and so one person has to stay aboard the spaceship, and the other ones go down in a little craft to check out the surface. And time for them, they feel like they're on the surface for like 6 hours, and in the spaceship, 10 years passes or something like that. So that's exactly what we're talking about, right? The idea that depending on your frame of reference, both time just literally does travel at different speeds.
Yeah, and that's why it's the fourth dimension. So on the space-time continuum, the space is the first three dimensions, and time is the fourth one. So it's just that it moves at different speeds for different people, just like you could be in a different position on Earth. Someone else could be in a different position in time.
What is, I don't know if this is directly related, but so the idea of a wormhole is some type of essentially a hole in space-time, right? That connects two different areas. Is that what a wormhole is?
Mm-hmm.
And that
Yeah.
has that, according to the theory of relativity or whatever, it is possible to have a wormhole, right?
Yeah, technically they're theorized to be possible, but no one knows how. So some
Okay.
people think maybe a black hole would be a wormhole. I don't really see that, because once you cross a black hole, you have the time problem that maybe you would go to somewhere else, but your time would have advanced infinitely far. So
Right.
I'm not super well versed in wormholes, but I know that
Okay.
people have thought that they may exist. In the movie, they thought they did. And
Right.
yeah,
Yeah, and that movie pretty well researched, but yeah, all of these things. So I mean, we have the mathematical proofs for the theory of relativity, right? This isn't just physicists coming up with random odd things, and they can prove these things mathematically, but
yeah.
all
Well, you
of
can
the
see them too.
right. Well,
Like
I
they
guess
do
with black
happen.
holes, right?
Yeah. Well, black holes and even on Earth, there's plenty of things in physics that your math doesn't work unless you include relativity. So it's pretty necessary for our modern view of physics that
Okay.
relativity exists.
Right. And but the implications of relativity are things that even physicists who can do the math, like a lot of these things just don't make a lot of I mean general sense. Like this idea of being able to, you said the twin paradox, that these ideas seem so incredibly foreign to us that it doesn't, like it's hard to conceive of a reality where these things can happen, wormholes and people aging at decades more than their twin or things like that. That's why these things are so interesting to the layman, is that they seem so foreign, but they're provable by math, and physics backs up this reality that seems so contrary to Newtonian physics, where it's just what we experience on a day-to-day level.
Yeah, it's a kind of interesting thing too, because when it was first discovered, people got a little overexcited about it, and there are journals out there that talk about how like this is one of the three people on Earth who understands relativity, or I think one of the first people who made that claim was a New York Times reporter or something, and was like, this is one of 10 people on Earth who understands special relativity, and then it just continued to get more ridiculous to the point where like at one point someone was like interviewing someone, they were like, you're one of three people, and they're like, well, if I'm one of three, I don't know who the third person is. But um, it really isn't that complicated. I think people just got a little overexcited about it. Undergrad physics students understand it pretty well. Even high school students can grasp it. It just takes a while to wrap your head around the fact that time doesn't advance uniformly for everyone. So
Right.
if people are interested in learning about relativity, I think um, it's a very approachable field, and sometimes people um, get scared away because they think it's too complicated. But after a little bit of thinking about it and practice, it really isn't that hard.
Okay.
Yeah, you kind of have to like untrain your brain of thinking the way that it, because our reality is what we experience, right?
Hmm.
So when we never have experienced this, because it's impossible for us to experience anything other than what our reality is, then that's why this types of stuff is so hard for us to wrap our mind around, because we can't do it, and therefore it's harder to think about. Like, it's hard for me to think about, well, how is a body that's, and then it gets into this time thing. Well, the body's processes are doing certain things, and like, why are those slowed down, or sped up depending on the speed somebody is going? And it gets very complicated and hard to understand unless you just remember that it's the time that's like really affecting everything, and the time is different for those two individuals. Then you can start understanding it better. But it is a hard thing to wrap your mind around. So I'm trying to, for all the laymen out there that are like, oh, I think I just had a seizure or a stroke. I did too, so it's okay.
Yeah. Yeah. I
Well, your
mean,
analogy of the body too, like your bodily processes don't actually slow down. So if you get on a spaceship and go close to the speed of light, your heart continues to beat at the same speed. Everything is normal for you. But if someone were to observe you, then it would look as though it were moving slower. So yes, your bodily processes don't slow down because of the speed. It's just that from other people's frame of reference, it looks like they do.
right. Yeah, thinking in
That
that.
might, maybe that
Exactly,
made it
and
more
that's
confusing.
where the migraines start.
Yeah, thinking in a new dimension is mind bending, but if you can bend your mind around it, like Peter says, if you get practice, you take a class in it, either in high school or college, and just practice thinking about it as a dimension or another, um, then then things start falling into place better. But yeah, trying to put the effects of relativity into your day, like map them into your current worldview without adding that extra dimension. That's when things don't make any sense and you feel like you're slamming your head against a wall. But let's talk about a couple other things before we wrap up this podcast. So one of the things, so I know there's been a lot of noise here in the last, I don't know, 5 years about a warp drive. I think they said theoretically that there's this idea that we could create a warp drive, essentially enough gravity that you'd bend space-time in front of the craft, something like that. Is that something you've read up on, Peter?
Yeah, it's a drive that's developed by a Mexican physicist called Alcubierre, and the Alcubierre drive is he developed this theoretical drive, and it was affirmed that it would work by physicists all over the world. But the issue was that in order for that drive to work, you would need the mass energy of Jupiter, which is essentially you would make Jupiter disappear and turn the whole thing into energy, which is a ridiculous amount of energy. So
Right.
on one hand, that's impossible. And the other problem was you need something called exotic matter, which is it's a type of matter we haven't discovered. It should exist, but we don't have any. So there were two big problems. The energy problems actually come down from what I've read recently to about the consumption of the United States in energy for 1 year or something. But
Oh.
while that seems much more reasonable, I don't know how you store that much energy on a spaceship. So there's
Right.
still problems with it, but it is theoretically possible, and you could go like 10 times the speed of light. The thing is, you're not actually traveling faster than the speed of light. Once again, we're bending our minds a little because the drive would use this exotic matter that they're talking about, and it would bend space to the point where it compresses space in front of you, and then you travel across that space instead of traveling across normal space. So essentially, you're kind of cheating. You're like, in no one's frame of reference are you moving faster than the speed of light, but if you actually look at where you started and where you ended, you would have had to have traveled faster than the speed of light to make that distance in that allotted amount of time.
Wow, that is crazy. Because, like you said, the speed of light and space, like it's an asymptote, right? Like getting to the speed of light is infinite, right?
Mm-hmm.
And so the
Yep.
idea that we can cheat our way around it seems almost like it shouldn't be mathematically possible.
Yeah, and we're not really we can't break the speed of light. It's a maximum speed because there is that asymptote for energy. It would take infinite energy to go faster than the speed of light. But if you, in a way, cheat it, you're crossing a shortened amount of space at a speed slower than the speed of light. But because you compress space so much in front of you, you're traveling across compressed space-time, or space if we want to just talk about it in terms of space. If you compress space to the point where it's 10 times smaller and then you move at 90% of the speed of light, now it looks like you've gone faster than the speed of light, because when you uncompress space, it's like if you take that blanket and you crumple it all up and then travel at your normal speed across that blanket and then uncrumple it, you're now at a different spot than you would have been.
Right. Yeah.
I read a
It's
book
weird to
about
think
this
about.
once.
Was it called A Wrinkle in Time?
A Wrinkle in Time, yeah.
Yeah. Yes, it's a documentary. It's I think we've discussed documentaries in this podcast before. Okay, it's not a documentary, just to be clear. Okay, so one of the things that, once again, I know we've touched on this, but still, it's hard for me to conceive. I know we're trying to say that time is a dimension. However, the idea of moving backwards in that dimension flies in the face of everything that, that kind of seems to ground any reality. The idea that, okay, I get the idea that at the speed of light I can move across distances, and in such a way that time doesn't affect me. But the idea that I could then take reality and rewind it seems to just be, it blows up everything concrete in the world, in my mind. But that is theoretically implied by moving the speed of light or faster, right? That you can move backwards in time.
Yeah, sort of. I mean, the reason it bends and breaks your mind is because it isn't technically possible. So you don't have to worry too much about it, because the speed of light is the limit. And for example, crossing a event horizon of a black hole is like that is like the slowest time can move, or fastest, depending on how you want to think about it. But like, you can't go any more than that. So
so the warp drive doesn't take that, and like isn't affected by this idea of I'm going faster than the speed of light, and then I'm compressing space. Time, those effects of time would still not be affected.
Yeah. Yep. So your time dilation, which is what it's called when time changes based on how fast you move, or the gravity, your time dilation would be affected by how fast you're moving, but that's the speed that you're moving, not the like apparent speed, right?
Got it.
So if you're moving at 0.9 c, or 90% of the speed of light across your compressed space, it would be affected by that 0.9, not your 9 times the speed of light or whatever.
Okay, got it. Okay. All right, and so you're saying
you don't have to worry about traveling back in time, because it's never going to happen.
Right. Okay.
There's actually something that I forget what they call it, but there's a cause and effect problem with that, where like, if you think about it, they thought that for a while neutrinos traveled faster than the speed of light, which if they did, then time would move backwards for them, which would mean like when a neutrino emitted by the sun went through the Earth, it would have yet to be emitted by the sun, which doesn't make any sense, right? Because
right, exactly.
Yeah. So there is a problem. They figured out that their calculations were wrong and neutrinos don't. But there was a time when people were trying to figure out how that would have worked, because they thought they moved faster than the speed of light.
Yeah, exactly. Yeah, I remember reading about that here, like, I don't know, was that 10 years ago when they did some measurements and thought that neutrinos had moved fast, had gone faster than the speed of light. But yeah, that does cause all of those issues I was talking about. Yeah, like all of those movies that you've seen about time travel, and where if you kill your mom accidentally, did you ever exist? Those are the same type of issues for neutrinos. So,
why would you kill your mom?
It is possible that someday in the future that'll change, but for now, we don't think it's possible.
Right. And why would you kill your mom, Johnny? It would be a bad idea, but
Yeah.
Generally frowned upon.
Okay. All right. One more question here. So this came up in a podcast, I don't know, like a year and a half ago when Matt was on. Matt's not available this morning, but Matt was talking about two beams of light traveling either together or away from each other, and the relative speed of those beams of light to each other. And it was explaining that those two beams of light approach each other at the speed of light, not 2 times the speed of light. Can you elaborate at all on that, Peter, and how that works?
Yeah. So relativity is the idea that basically, from your frame of reference, basically in relativity, you are the center of the universe, and everything in the universe moves around you. So the first way to start thinking about relativity is to think like, say you're in a car moving down the freeway. It's not you moving down the freeway, it's the Earth moving under you. So you get in a spaceship and take off to Mars. It's not you moving off of Earth. It's Earth moving away from you and Mars moving towards you. You're just motionless, right?
So this is like the point of reference most celebrities, for example.
Yeah, exactly. You're the center of the universe.
Right, exactly. Okay.
It's a very egocentric way to look at the universe, but it's kind of the first thing you have to realize when you start to think about relativity is you have to think of everything moving in respect to you, and you are motionless, and that's it. So,
do you think I can tell my wife this today and just tell her I'm just practicing relativity, and so everything revolves around me today?
Probably not a good policy.
I mean, you wouldn't be wrong either. So
exactly. Okay.
From your frame of reference, everything is moving relative to you.
Okay.
And when
one
her
way to think about it is
me, then it will be, since it'll be approaching the speed of light, this can get really complicated.
Okay. All right.
If you one example people have of relativity, this is like a really simple example, but like you get in your car on the freeway and you look at cars going the opposite direction on the freeway and it looks like they're going really fast because you think of yourself as motionless and the cars. So if you think of yourself as motionless, it looks like the cars going the opposite direction on the freeway are doing 160 if you're both doing 80 miles an hour. So the problem is with that, though, as Matt was describing a year and a half ago or whenever you guys talked about that, is say that you're going at the speed of light and say you're a photon watching another photon come towards you. If, as we talked about with that freeway analogy, you're doing 80 and they're doing 80 and it looks like 160. If you're a photon of light traveling towards a photon of light, then it would seem like they're doing 2 times the speed of light, right? That just seems to be what would happen. However, there's some equations that actually solve this problem because you don't even have to be going the speed of light to think about this. You could think of a spaceship traveling towards another spaceship, and both of them are doing, say you're in a spaceship and you're going at 90% of the speed of light and you shoot a missile at 90% of the speed of light. That seems like we would run into the problem of you add those 2 velocities together and now it's faster than the speed of light, right?
Right.
Or you shoot a laser and you're adding the speed of light to yours, so you'd be going 190% of the speed of light. The problem there is you can't violate the speed of light from any frame of reference, no matter what frame of reference you're in. So there's some equations that look kind of like the Doppler shift equations, but they will let you figure out how fast it would be moving. It's kind of a hard thing to describe without going through the actual math of it, but
okay. But from no point of reference, are things going faster than the speed of light, right?
Yeah. No matter what you do, no matter what frame of reference you look at, they'll never violate the speed of light.
Okay, so like even if I'm an observer, I'm sitting on Earth and I'm looking at lasers shot in opposite ways. They're relative to each other. Everything's still just bound by the speed of light.
Yeah.
Okay. Interesting. Okay. Any other tidbits, Peter? Any last words on the theory of relativity?
I think that there's some interesting stuff with light and relativity, so maybe it would be worth talking about that really quick.
Sure.
Because light isn't affected by gravity, relativity is the thing that explains why it bends. So, and this is once again another example of why waves are both light, or particles and waves. When light moves towards, say, a black hole, and one part of it is deeper in the black hole's, like, quote unquote, its gravity well, the deeper part now has a slower, like, time advances slower for it than the part that's further out of the well. So the reason that light bends around it is because part of that wave is moving at a slower like time advances slower for half the wave than the other half, so it bends because one half is moving faster than the other half. Like if your wheels on a car were moving faster on one
Okay.
side than the other,
Huh.
that would be why your car would turn as well.
That's crazy.
It's kind of interesting to think.
Yeah.
I think black holes are fascinating to think about because they're kind of the extreme with relativity.
Yeah, and I think the last physics podcast that we had I said quite a while ago, we mentioned one thing about black holes that I had read an article, this now probably 2 years ago, where it was talking about how inside the event horizon of a black hole, theoretically there's this area where space-time is being dragged by gravity at the speed of light or something along those lines. So essentially inside of that space, you could travel and theoretically you could break I think it's kind of like the idea of a warp drive. Like now all of a sudden I'm traveling further than light would in a particular time. That's because space is already moving at the speed of light, and I'm inside of that space also moving. I don't know if it's something you've read or seen, but this is an article I read like 2 years ago, just talking about the theoretical issues and complexities of being inside that event horizon and that super massive gravitational pull of a black hole.
Yeah,
Anyway.
Once you cross that event horizon, time, well, from an outside perspective, people watching you, time seems to stop moving, which
Right.
If time stops moving, now you're in a three-dimensional world, which is what we all think we live in, but we don't. So
Right.
I guess it becomes a problem because now you took out one of the dimensions that we all take for granted. And
Yeah.
now things don't make sense anymore when we're in this three-dimensional world we thought we were in.
Right, exactly. And that's what Johnny was talking about earlier, as far as just saying that's where, it takes some practice thinking around those, and there have been incredible physicists in the past that do that really well, that have a lot of practice, and therefore are able to make these connections and come up with these ideas and formulas and theories that explain things, because they live in that world where all of these things make sense, where the general population is lucky if we can understand like some type of implications, or if we can even, like you said, you can plot that there are formulas that help you kind of figure these things out and make sense of them, but mapping them into your world experience and being able to come up with the other potential theoretical implications of black holes and the relativity and space-time and all those things, that takes an understanding of physics that the layman doesn't have. So, okay.
Yeah, it becomes very hard very quick, but it's always fun to talk about and think about.
Yeah, exactly. Yeah, good times. All right, I think that's pretty much it. Johnny, I hope you've told your wife that you are the center of the universe.
I'll let her know for sure.
Good luck with that. All right. Well, thank you. Thanks, Peter. Thanks, Johnny. And join us back again for our next podcast.